Hello everyone. My name is Dr. Mihir Ghosh. I'm from the Department of Chemistry, SRM Institute of Science and Technology. I hope you enjoyed my first two videos regarding coordinates in chemistry. So this is the third part of my video. So we will start beginning the discussion about the spectrochemical series. What is exactly the spectrochemical series? In the last video, we have discussed why we need the spectrochemical series. So this is a series which arranges the ligands from weak fill to the strong fill. Halides and water are generally weak fill ligands, while cyanide, carbon monoxide, phosphanes, some nitrogen ligands, all are coming to the strong field ligands. So this is exactly the series. So from here to there, so it's less. So the splitting ability decreases. Here we are showing here the complex having different kinds of ligands. When the central metal atom is same, how exactly the splitting energy varies. Here we are showing here CrF6 water and H3 CN. If we compare this all these ligands CN, NH3, H2 and F, we can see they are in a sequence. CN is in the exactly the right. Then next is the NH3, it is here, and then next water, and then F minus. So here we this in this from this using this spectrochemical series easily we can identify which complex will show better splitting, better crystal clear splitting. This is the use of the spectrochemical series. Besides the spectrochemical series, we can see some change in color change with ligands. Different ligands produce different splitting energies and therefore different colors. For example, replacing water ligands around copper 2 with ammonium change of the color is also it is more intensified. Now about the CFEC. Now we know the crystal field splitting energy. What is the crystal field splitting energy or stabilization energy? This is extremely crucial. CFEC is the energy gained by electrons when electrons occupy lower energy d orbitals after splitting. For octahedral complex, CFEC is calculated using zero point 0.5 times T2G electrons plus zero point 0.6 times Eg electrons multiplied by the delta O. This is the final formula of the CFSE calculations. This is the final formula of the CFSE calculation. Let's start with the D1 system. So D1 system, this one, only one electron is here. So the splitting in the T2G levels, that this is the T2G, this is the PG. So in the T2G level, we can see only one electron. So 1 into zero point 0.4. So the final energy is zero point 0.4 delta O. As there is no electrons in the T2G level, same way we can see if we make it like a 2 electrons, we can have a 2 into zero point 0.4, it's 0.5, 0.8 delta. So 3 into zero point 0.4, 1.2 delta O. So based on how many electrons are present in the T2G and EG levels, we can make their corresponding CFSE calculation using this CFSE formula. This is the clear representation how exactly D1 to D12 D10 system, how exactly the electron distribution exactly takes place. This is extremely important. Look very carefully. So this is D1, it have no other option. This is D2, no other option. It is D3. The problem exactly start from the D4. So the fourth electron have two options. Either it can go to the TEG levels or it can make the binding to the T2G levels. Same thing for the D5, D6 and D7. Now how we will decide the fourth electron, fifth, sixth and seventh electron, which configuration should be preferable for the specific complex, either this or this. So this is called the high spin complex. This is called the low spin complex. So when it will favor the high spin complex and when it will favor the low spin complex, it is completely based on the splitting energy. Let's say if the splitting energy, that means let's say these energies extremely high, it will prefer to bind up here. This is more preferable for the electron. But if this energy is very less compared to this one, then it will prefer to go up here. So the point is very simple. If this energy is very high, the T2G and EG levels, this T2G and EG level, it is very high, it will prefer to bind up here. And if the energy levels are very close to each other, it will prefer to 1, 2, 3, then 4 here. That means it will prefer to go to the EG levels. So that is why we can see different kinds of possibilities. Again, from the D8, 9, and 10, there is a tail, whether it's a low spin complex or the high spin complex, it will remain same. There is no option or no choice to go to the electron to choose it is a low spin and high spin. That's why D1 to 3 and D8, 9, 10, we cannot see any kinds of high spin, low spin complex except D3, 4, 5, 5, and 6 systems. Okay, it have to be remember. It's extremely careful. So we have to see here only one thing, that is called the, it have to face the pairing energy. So when the pairing energy is high, so the when we can see the delta is high, it will follow the low spin complex. It will the smaller delta. It will follow the high spin complex. Okay. Now here it comes the concept of the pairing energy. Pairing energy means when the electron follows the pairing in the T2G levels. So when a electron prefer to go to the from T2G to, let's say this is T2G and this is EG. So one electron preferred to either trap to pair up or it will go to the higher level. It will based on the one factor that is called the pairing. The pairing means making pair, how much energy is utilized to make the bonding. So when there is two electron, both electron will repel each other. Okay. So that means when they will repel each other, so one electron have to change their orientation in the opposite direction. Then only in the same orbital it can bind. So this is called the pairing energy. So using this pairing energy, it can make the change the spin and finally they can bind to the T2G levels. But if this pairing energy is very high compared to to the electron preferable energies to going to the EG level, so it will prefer to going up here rather than pairing here. So the basic way, the simplest way, if I want to say, whatever is less energy, it will prefer that one. So if pairing energy is high compared to the delta O, it will go to the higher energy levels. So that means it will show high spin complexes. But if delta O is high, that means the electron have to overcome from T2G to EG levels with very high energy. That is high compared to the pairing energy. It will prefer to pair up here. If it pair up here, it will show the low spin complex. So high spin, low spin based on the total number of unpaired electrons. We call it a complex. It's a high spin, not a low spin. So based on the total number of unpaired electrons, we can decide whether it will go to the high spin or low spin. Okay. So in a summary, if we say if P is delta greater than delta, the configuration T2G3 EG3 is preferred. This is known as the weak field or high spin situation. If delta O is greater than P, the configuration prefers T2G4 EG0. This leads to the strong field or low spin situation. I hope it is very clear for you right now. Now we are showing from D1 to D10 all possibilities of arranging the electrons and their corresponding CFSE levels. Okay, D1 to D10. Okay, do you want to detain, and the corresponding high spin, low spin, and the corresponding CFSE levels. So you guys can do one thing very carefully. Just do you want to detain? You just try like like, and just finally just create make the calculation and see exactly whether it is matching with your this CFSE value or not. You can do it in your home. Okay, it's very good to calculate how CFSE from your side to check it whether you can calculate the CPS energy very carefully or not. Okay, now let's discuss about the square planar and octahedral. So if we see the D2G and EG labels like this, and square planar are usually like this. Now about the magnetic properties and metal complexes. So um, magnetism mainly arises from the unpaired electrons. If there is like all electrons are paired, so with no magnetic moments we can see. Okay. But when there is number of unpaired electrons, due to their magnetic moment, we can see there some magnetic properties. Okay, as we know, electrons are charged particles, so they can they're moving particles as well. So they can so these particles can be the current of electrons through an electric wire of the movement of the charged particles with an atom. These charged particles move much like planets in a solar system. So the total magnetic moment we can calculate with a very simple formula. This is called the spin formula calculation, where n is the total number of unpaired electrons present in the system. N under root n into n plus 2. This is the formula. Using that one, we can calculate the magnetic moment of a unpaired electron system. So if we calculate this magnetic moment, so from D0 to D10, these are the calculated values. But somehow, when it was observed experimentally, it was observed these values are somehow matched in the initially up to D5. Then there is a sudden jump, sudden change in the observed value. That means it's not exactly matching with the calculated value. If you see these values, there is a huge change. So why specifically these changes are happening? So later on, the scientists discovered this is actually the spin orbit coupling. So what is a spin orbit coupling? So spin orbit coupling means like when an electron moves orients to its like own axis, uh, as well as same time it's rotates outside of the nucleus. So when the electron can jump from one orbital to another orbital, then this due to this jumping, the magnetic moments having gets changed, and this change we call it like a observed value. We see there is a huge sudden change in the magnetic moment values. So due to that one, we see a sudden jump. We call it like a magnetic moment value, observed value. So that's why you see there is a sudden change. So due to the jumping of the electron from one orbit to another orbits. Okay. So some examples are given here, and so magnetic properties of the coordinate complex. We're showing some example here. K2COCl4, COH2 Cl2. So now we can say no spin orbital contribution. So that's why in the first case we can see the magnetic moment is 3.73 Bohr magneton. Okay. But where as we can see the due to the orbital contribution, the magnetic moments gets changed to 4.2 Bohr magneton, higher than the spin only value, because all having the total number of unpaired electrons same. Here is also 3, here is also 3. But due to these contributions, their magnetic moments gets changed from 3.73 to 4.2 Bohr magneton. So spin orbital contribution we can showing here exactly how it's the electron jumping is exactly happening here. For the first row, d block metal in the metal ions, the main contribution is due to the magnetic susceptibilities from the electron pair. However, there is also an orbital contribution from the motion of unpaired electrons from one d orbitals to the another. This motion constitutes an electrical current and so creates a magnetic field. So you can see here this way the electron jumps from one orbital to the another one. Some other factor is also there, temperature dependence of the magnetic moments. So in high temperature, you can see magnetic moments also gets changed. Now about the ferromagnetism, antiferromagnetism, and charge transfer complex. Finally, the charge transfer complex. And the charge transfer complex, we can see the transfer of charge from one metal to the another metal, another to the ligand. So for the KMnO4, we can see the charge transfer is possible, or to K2Cl4 charge transfer is possible, but the KClO4 without having the Cl atom, no d orbitals, it cannot do the charge transfer. So that's why we can see the white in color. However, for the KMnO4 and ClO4, Mn and Cl are having the d orbitals, so the d orbitals having d orbitals, the ligand, that means from O minus, the ligand can transfer their electrons from their O oxygen minus to the pre-D0 levels of the manganese and chromium. So that's why due to the transition, those have some intense color. Same for a potassium dichromate as well. But KClO4, as Cl does not have any kind of d orbital, it cannot show any kinds of specific color. However, they looks like same. Their chemical formula, but without having the d orbital, Cl cannot show any kinds of transition. So that's why we see the KClO4 as a white in color. Now some of the disadvantage also, safety is also there. Okay, now that's it. And this is one problem. I guess you enjoyed my video. So if you want, you can try this one also, this problem. Okay, so that's it for the potential chemistry. And if you have any doubts, please ask me in this video in the comment box. I will be happy to answer any kinds of questions. Thank you, everyone. See you in the next video. Bye bye.